Welcome back, Nature and Code. We're in chapter 7. We're speaking of natural selection, and we just established this framework here where, depending on the fitness of the heterozygote, we get three different types of natural selection: directional selection, balancing selection, and disruptive selection. And these three different types of selections, which we're going to study now, are basically dependent on the fitness of the intermediary genotype. So if the heterozygote fitness is higher than the other two fitnesses, then we have this fitness peak, which gives rise to balancing selection. If it is lower than both of the homozygote genotype fitnesses, then we get this fitness valley, which will give rise to disruptive selection. And any case in between will give this sort of slope here, and that will give rise to directional selection. And so what we're going to do now is we're going to implement this in code, but we're not going to implement stochastic simulations that we have before. We're going to just plot two things. One of those things, the first one is going to be, we're essentially going to plot delta p, so the change in the allele frequency, and remember this is fundamentally evolution, as a function of p. So given p, some value between 0 and 1, given the allele frequency now, what is delta p going to be in the future? So what is delta p going to be given p, I should rather say, because if it's positive, it means p in the next generation will be larger, and if it's negative, then p in the next generation will be smaller. And then based on that, we will implement a deterministic simulation, so that's purely based on these frequencies and on math. There's no stochastic effects, where we will have time here, and we will plot p over time. So let's go ahead and do that. So why don't we start here with our code that we developed here. We won't need this code, but we will need, the HTML template around it, and we will need the D3 and draw line chart function. So why don't you just take this here drift and selection code example that we still have open, and just save this as another file, and let's go ahead and save this as delta p versus p, because that's what we're going to plot here. Okay, so save this, and then basically you can get rid of this code here. Don't get rid of the draw line function up here, but just get rid of everything below that. Okay, so let's go ahead and implement this. So we need to define the selection coefficient, and I'm just going to set this here at 0.1. And then we need to define our heterozygous effect. And I want to start with directional selection. And as we now know, directional selection will occur when this value is between 0 and 1. So I'm going to set this to 0.2. Okay. And since I'm going to plot a line, I have to have this data array here that I'm going to fill up with values. Then I'm going to initialize this as an empty array. And now I would essentially like to, generate the values for this array so that I can hand this array over to the plotting function. So what will the values be here? Well, previously the values were just genotype frequencies or allele frequencies. And, in this case, since, as I've shown here on the slide, I would like to plot delta p, I have to push the corresponding delta p values into the data array. And just as a reminder, delta p can be calculated using this formula here, right? Which, admittedly is a bit complicated, but it's actually quite easy to implement in JavaScript. Okay, so let's go ahead and do just that. One other thing that is going to be a bit unusual in this case is, we have to ask ourselves, well, okay, what are the steps here? Because previously they just used to be generations. Now they're going to be values between 0 and 1. And, we just have to agree basically on the small increments that we're going to use here. And I would say, probably, we can start with 0.05 0, 1. So start with 0 and then increment each of these values with 0.01 until we reach 1. And then see if that is good enough. Okay, let's go ahead and do that. So I'm going to set up a loop for var I equals 0, and then later I'm going to use this I as my P. So I want I to be smaller or equal to 1, right? So we're going to stop at 1. And as I said, we are going to increment by 0.01. Okay, 0.01. All right. So as I just mentioned, our P is essentially whatever we have in I. Q, as always, is 1 minus P. And we have defined S and H up here, so we have all the 4 variables that we need to calculate delta P. So var delta P equals. And now we simply have to implement this formula. And that formula is sum numerator divided by sum denominator. Okay, and I'm going to put these in parentheses right away. Okay, now the numerator was P times Q times S times, and now I'm going to put this here in parentheses. We have pH, so P times H plus Q times 1 minus H, and so I'm going to put this 1 minus H here in parentheses. So make sure you keep track here of the parentheses. So here we got 1 opening, 2, 3, and then those 3 close again. So that's fine here. And so over here, the denominator is simply 1 minus 2 times P times Q times H times S minus Q 2 times Q times S. Okay, so that's the formula. It's actually quite simple, right, if you need to implement this in JavaScript. Okay, so now we have delta P. Just going to go ahead and push this into the data array. And that's it. Delta P. Okay, so for a P value that starts at 0 and gets incremented by 0.1 until it reaches 1, we're going to calculate delta P. We push this into the data array, and now we would like to plot this data array. So we're just going to call the draw line function, the draw line chart, as it's called, function. And we're going to pass in the data array as always. Our X label on the X-axis should be P. And on the Y-axis, we have delta P. So we can either write delta P, or if you want to be more sophisticated and you actually want the Greek symbol, you can use the Unicode, corresponding Unicode symbol, or Unicode representation, which is \U0394. Okay, that's the Unicode code for Greek delta. And then I'm going to add as the 4th parameter this empty array because I don't want a legend. Okay, now let's save this and go to our browser and open the corresponding file. This is still here, our drift and selection. So open file, chapter 6, delta P versus P. Okay, so open, and here we go. So it plots the correct values. However, there are 2 problems here. The first problem is that this seems to suggest here P is going from 0 to 100, but we really only want it to go from 0 to 1. Well, the reason is, the function simply looks at the data array and plots the values of the data array And down here, it just essentially plots the index of the data array. And so far that was quite okay because that was simply, the generation, for example. However, in this case, that's not true. We actually want this range to be from 0 to 1, not from 100. Well, it turns out that, in the earlier video, when I first introduced this function here, draw a line chart, I said this has 6 arguments, but let's not worry about the last 2 arguments. You don't have to pass those in, and the function will do whatever it needs to do, and that's correct. However, these 2 arguments, they're actually specifically for situations like the ones we're now encountering. So this xmax is exactly for a case where you don't want the function to just plot the indexes of the data array, but rather you specifically want to say, these values need to go from 0 to some other value. So let's pass that in. In our case, that value is 1. So let's pass in 1. Okay, so let's see, save this and reload. And indeed, okay, so this is now correct. It goes now from 0 to 1 as it should. The other example, though, the other problem, rather, I should say, is that, it does plot the correct values, but those values are so small, it doesn't make sense here to span the y-axis from 0 to 1, which is the default. And so once again, if you go and look at this function, the 6th parameter here is actually, takes care of that. So it's a bit like xmax, only that it's ymax. The problem is, however, often that you actually don't know what your ymax is going to be, right? This could change depending on, whatever you're calculating. And so that's why I introduced this ymax flex. This is a Boolean value, which, if you don't pass anything in, it assumes it's false. But if it's true, it just goes through the array and takes a look, finds out on its own what is the maximum value, then adds a little bit of margin to that, and spans the correct y-axis. So this is pretty handy and convenient. So all you need to do here is to basically say true, pass in a Boolean value that's true, and it should take care of all the problems here. So let's go ahead, reload this, and indeed, that's exactly what happens. It figures out that the maximum value here is something like 0.015 or 0.016, and then it just adds a little bit to that so that, there's a little bit of room here. Okay, so this looks almost perfect. Okay, why do I say almost perfect? There's one little gotcha here that I want you to be aware of. Take a look at this. So here it says 1.0 because that's the maximum value. But then here, as you can see, the delta p is just a little bit larger than 0. And that doesn't make any sense, right? Because once we're at p equals 1, we can't have a positive delta p because there's nowhere to go. So this needs to be 0 here. Why isn't it 0? Okay, and that's actually a subtle problem that has to do with rounding errors. Let's go ahead and console log I here. So let's print the value of I into the console. Console log I. And let's take a look at what's being printed here. Okay, so reload this, and then of course view developer JavaScript console. All right, and if you scroll down here, you see a couple of things. First of all, you get our old friend, the rounding error. Okay, and the second problem that you see here is that it stops at 0.99. Something, 7 here at the very end. And that seems strange, doesn't it? Because if we go back to the code, we said, I should be smaller or equal to 1. So why doesn't it go up to 1? Because we said equal to 1. Well, it's exactly because of this rounding error here. If we add another 0.01 here, we would get 1.000 and so on 7, and that, technically speaking, is larger than 1. And so because of this rounding error, this function here, or this loop here, gets terminated too early, just a little bit too early. And so here we're not actually plotting 1 over here. This is actually the value for 0.99. So let's go ahead and change this. So the trick here is to basically say, just go a little bit above this maximum that I want here. Okay, just some sort of buffer for this rounding error. I'm just gonna, set the maximum value here in an xmax value variable. I'm gonna save this here as 1 xmax, and now I'm just gonna say here, okay, that value xmax plus some buffer, very small buffer. It doesn't really matter how small it is. I guess just as long as it's certainly smaller than this value. So I'm just going to say 0.005. You could take a much smaller value, but that's fine. And then, here in principle, you could also make this more generic and say, rather than hard code 1 down here, what you really want to pass in here is xmax, right? Because that's what you want. That's what you want to span the x-axis to, which happens to be 1, of course, because I define it here as 1. Okay, save this. Go back, and now it does go up to 1, and if you look at the code here, at the figure here, it's correct. So let's close this here, and we can now see here the correct graph. Okay, so this is the correct graph. Now what you can see here, once we sorted out these technicalities, is a simple phenomenon. That is, whatever p is, delta p is going to be positive. And that is directional selection. It means that it doesn't matter where we are, in the space here of p. It doesn't matter what the frequency of A1 is in this generation. In the next generation, it's going to be larger. And that's natural selection, right? It's a very specific type of natural selection, which is called directional selection. And it's called directional selection because it goes in only one direction, and that's up. In this particular case, with these particular parameters, it goes up, 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 and then p will reach 1, and that's the end of the story. And if you look at the slides here where we had this directional selection, that makes sense, right? We're here on the slope, and whatever we're starting with p, we can only go up because the A1 has the highest fitness, and so the population will go to this, through this slope here to this genotype which has the highest fitness. And since the heterozygote has the intermediary fitness, there's going to be no complications. It's just up the slope. And so that's exactly what this graph here shows. Now let's quickly build the second graph, which is quite similar. Now though, we're going to have here the generations on the x-axis, and here we are actually going to plot p. So let's go ahead and do this. Once again, let's take this file here because it's going to be quite similar, and let's save this, save as. So in this case, we're going to have p versus time. Okay, so we are going to keep these S and H values. We have to change a few things here. What we need is we need to define what we're going to start p with. So I'm going to set here var p to 1%, okay? 0.01. Var data, that's still fine. We don't need the xmax anymore. And now we're going to say for var I, just like we did before, I smaller than, however many generations we want. So let's go ahead and actually set up a variable generations. And then I equals I plus 1. So I'm going to do this here, var generations, and let's say we do 400 generations. Okay, so I can get rid of the console log here. So var p, well, what is p? Well, we've defined it already up here, so let's not worry about this at the moment. Okay, var q is still 1 minus p. That's fine. The delta p formula, of course, is still the same. And now we simply need to update p, right? So we just calculated delta p, so p is going to be whatever it was before plus delta p. Okay, delta p. And now we're going to push p into the data array, because that's what we want to plot on the y-axis. Okay, so this should work. The only other thing that we need to change is we need to update here the parameters here. So on the x-axis, we now have again essentially the generation. On the y-axis, we now simply have p. We don't want a legend. And this can go on for us however many generations we have. So if you want to pass that in, you can just say generations, but it actually wouldn't be necessary here because it would just automatically do that. And the values between 0 and 1 seem like a good default. So let's go ahead, save this. And now let's open this file. I'm going to just open a second tab here in the browser, and I'm going to open this file. And let's just see what happens here. P versus time, that's the one I want. Open. And here's what this looks like. We start at 0.01, and then over time, we quickly go to fixation up here. And so these two graphs, right, are now deeply related. So here you can see this is where we would be at 0.01. And then we simply add this delta p to p, so then we would be over here. And then we add this delta p to p, so then we would move a little bit to the right, and so on. So we consistently keep on moving to the right. And this basically, the larger this value here, delta p, the faster we're moving to the right. And so that's exactly what you see over here. In the beginning, suddenly this goes very fast, right? And then as soon as we reach a certain value, say somewhere between 0.5, 0.6, and you can see here exactly where this happens. It actually happens a little bit earlier. But, you know, it seems to, so here, mathematically speaking, the slowdown starts happening here between 0.3 and 0.4, because that's where you reach the maximum value. And now the delta p is actually going down, which means it's still positive. So we're still slowly moving to the right here over time, but we're doing so at a slower, increasingly slower pace. And this is exactly the sort of slowdown here that you observe. And you get this classical S-curve here, where in the beginning it's slow and then suddenly it takes off and then it slows down again. And so this is directional selection. It's sort of the core example of natural selection. It's how we usually think of natural selection. Like you have a rare mutant, it takes some time to get started, but then very quickly natural selection will do its thing and it will bring the allele to fixation. This is directional selection. It's quite a common phenomenon, of course, but as we'll see now with this code, we can look at the two other types of selection, which are a bit more tricky, and we'll do this in the next video. See you there.